So here we have a second order differential equation with constant and non-constant coefficients. The coefficients are functions of x. Do we have a problem here?
It's
When it
left.
started recording it.
Oh, I see. All right, so we have non-constant coefficient second order differential equation. And it also has the problem of singularity because at x equal to 0, this vanishes, right? So you know that the ordinary power series solution wouldn't suffice. Okay, therefore, we need to use the Frobenius method. So let me retrace what the Frobenius method was. The Frobenius method was to use y equals to sigma n from 0 to infinity of an x to the n plus r as the solution type, where this r could be any real number. It could be a fraction, it could be a negative number, it could even be square root of 2, whatever. Okay? And somehow there are cases where you can find solutions of that form. Now, last time I concluded with a formula that gives us the value of r. That was called the indicial equation. What was the equation? That was indicial equation was r times r minus 1 plus p naught r was q naught equal to 0, where and then I actually had to explain what p naught and q naught is. P sub 0, q sub 0 are special values of the function p and q. So let me show you how you apply the indicial equation and all that. Okay. So this will be the standard way you would solve from now on. So solution. First, you divide everything by x squared. And from here, you're going to call p of x, the capital P of x, as 5x over x squared, and capital Q of x as 3 minus x over x squared. So this one is called capital P, that's called capital Q. Now, you should also simplify it. See, you have an x here, x squared there, so you can cancel the x's, right? Leaving you with 5 over x. Okay? Now once you have that, then your small p of x is defined as x times capital P of x, and therefore if you multiply x to 5 over x, x's will cancel and you're going to get 5 as your p of x, right? And small q of x is defined as x squared times q of x, and therefore x squared times 3 minus x over x squared. These will cancel, leaving you with 3 minus x. And once you have them, p sub 0, or p naught, is defined as the function small p valued at 0. Well, this is a constant function, so no matter what value that you plug into x, it doesn't care. It's always 5 for our example. But sometimes you will have a function of x where you do have to plug in 0. For example, q of x. Q of 0 is q sub 0, which is taking this function 3 minus x and plugging in 0, so you get 3. Once you get these values, then you put them into the indicial equation. Indicial equation gives you r minus 1 plus 5r plus 3 equal to 0. Which if you simplify this is r squared minus r plus 5r plus 3 equal to 0, and r squared plus 4r plus 3 equal to 0. Those solutions are r plus 3, r plus 1. It factors as that, therefore the solutions are negative 3 and negative 1. Once you solve an indicial equation, yes?
When you're trying to find the small p, small q, you just multiply by the denominator? Or do you always
No, you always multiply by
x
x and x squared.
Okay.
It's always, this is not regarding to denominator at all. I just made the functions easy so that they cancel. Yeah. But in general, you always multiply by x and x squared. Okay, so when you have the solutions of indicial equation, there are some things to consider. If they do not differ by an integer, in that case, they both will give you one solution each. And you end up with a solution for two linearly independent solutions for this, for each individual value of r. And that's how you solve the difference equation. Now, when they do differ by an integer, then there are some cases where you may not be that lucky. You may end up having one of them failing to give you a solution. Just like when we tried to plug in the regular power series into here and found out that the only way you can get the solution is to set y equal to 0 entirely. So that was how you failed, right? So something like that could happen for one of them. And we actually know which could fail. The smaller number could fail. Nowadays, sometimes they don't fail, and actually they give you both solutions at once. But sometimes this one can fail. Okay? So often on the exam, I would give you a question like this one and say, find one solution of Frobenius type. Okay? If that's the question, then you would solve the initial equation and then choose the higher number. Okay? You choose the bigger number for the value of r, and then you're going to proceed to solve it. Okay? Does that make sense?
Always choose the higher number.
Always choose the higher number. Okay? Some people like to choose the lower number because if you choose the lower number, sometimes you get the entire thing. Yeah, but the problem with the lower number is sometimes when they differ by integer, sometimes you have to modify the solution by this times ln of x. So there's a logarithmic singularity somewhere. We're not going to go there, but that's what could happen. It could happen that for the lower value of this r, you don't get the regular looking Frobenius type solution. You actually have to put a log there somehow. Okay. So let's now choose r as the bigger number and proceed to solve this equation. So all this work was to find out that the value r equals to -1 provides one possibility of r. So we're going to set r as -1 so that y is sigma n from 0 to infinity of an x to the n minus 1.
Choose the higher number.
Yeah, you choose the higher number. -3 and -1. -1 is bigger than -3. You choose higher number. Okay, now you just plug everything into each individual ones. Okay, so let's see. For the first one, it's x squared What do you get if you differentiate twice? First, n minus 1 comes down, and that turns into n minus 2. Then another differentiation will give you n minus 2 there, and leave you with n minus 3, right? So that's what you're going to have for the very first one. Plus 5x times, if you differentiate just once, you're going to get n minus 1 times an, x to the n minus 2. And then for this one, you should multiply them out, and then write 3 times sigma n from 0 to infinity an x to the n minus 1, and then minus x sigma n from 0 to infinity of an x to the n minus 1. So that's what you get after plugging this thing in. Now in the next line, you should multiply these two inside. So x squared times x to the n minus 3, because the exponents add up. 2 plus n minus 3 is? What's that?
N minus 1?
Yes, n minus 1. Okay, how about this one? It should be 5 n minus 1 an x to the n minus 1. And by the way, I noted this before. If you plug in 0, these don't become 0 at all. So contrary to the case when we are doing for the ordinary ones, when we were doing the regular power series ones, whenever we differentiated, we made the n start from 2 or 1, right? That doesn't work here. Okay? You don't do that here. In here, you always start from 0 for the Frobenius method. Now 3 goes inside. Yeah, plus minus an x to the n. So that's what you get. All right, now which one needs shifting?
Last one.
The last one. What should I replace n by?
N minus 1.
N should be replaced by n minus 1. And since I'm lazy, I'm just going to rewrite this one. So n should be replaced by n minus 1, n minus 1. Even this one, n minus 1 is equal to 0. That's what you have to do. What do you do? N minus 1 equal to 0. If you solve that for n, what happens? N is 1, right? N minus 1 equal to 0. If you solve for n, you get n equals to 1, right? So you replace this by n equals to 1. So doing all that finishes the shifting. Okay? If you're not sure if you shifted it correctly or not, one thing you can do is to actually write them out. So when n is 0, you get x to the negative 1 times a0 times negative x. Multiply that out. And when n is 1, you get a0 negative and x to the 0th power, right? See if they match. Okay, they should exactly match, because we're not replacing one by something totally different. They should be producing the exact same terms. I'm just rewriting this in a different format so that every power of x matches with each other. Okay, so all of them has x to the n minus 1 as the n minus 1 will be the power of x. Okay? In other words, what I'm trying to do is I'm trying to combine the like terms. Okay? To combine like terms, the powers of x should be the same. Right? Okay. Now we look at what happens when n is 0. So we use this factory worker analogy. There are 4 factories. Each individual factories produce terms. And at the 0th hour, the first 3 factories are working, whereas this one starts working at the 1st hour, right? So only these will produce terms while this is resting. And let's see what happens in that case. When n is equal to 0, you get negative 1 times negative 2, a0, x to the negative 1, plus, when n is 0, you get negative 5, a0, x to the negative 1. Okay, and then plus 3, a0, x to the negative 1. That's what you get from these three factories. Okay. And then in the next hour, starting from n equals to 1, all of these start producing terms, so you can just combine them into a single thing, because now they all follow a pattern. So plus, so this is what happens at n equals to 0. This is the only exceptional case where only parts of all the four factories produce terms, but after that, all of them always produce terms. So I can start by saying n equals to 0 through infinity, no, 1 through infinity of all of these combined. And I can even, when I combine them, I can even factor out the x to the n minus 1 because they're all the same. So I can do n minus 1, n minus 2, an plus 5, n minus 1, an plus 3, an minus an minus 1 times x to the n minus 1. Okay. And I keep saying this, but I wrote down an equal sign here, right? So if you actually had the patience to write down these individual terms for n equals to 0, 1, 2, 3, 4, maybe up till 10, and if you wrote down the individual terms for n equals to 0 up till 10, you'll see that they both will give you exactly the same thing. Okay? So I'm not really hiding anything under my sleeves or anything. There's no magic here. They're exactly the same thing. It's just written in a different way. Okay. Any questions so far? Yes?
For the what's it called, when n equals 0, they come out as v0.
Yes, that's a good observation there. That's a great observation. If you did it, this is plus 2, minus 5, plus 3. 2 plus 3 is 5, minus 5 is 0, right? They all have a0, x to the negative 1 as the same thing, so this part becomes 0. Okay? Actually, that's the feature of the Frobenius method. If you recall, the indicial equation, this thing here, was obtained actually by first assuming that a0 is not equal to 0. That was our initial condition, one of the conditions for this one. And under this condition, when we wrote down the case for a0, a1, a2, n equals to 0, n equals to 1, we did that. We realized that when n is equal to 0, it produces something times a0, and saying that a0 is non-zero and the other parts should be 0 gave us this indicial equation. Okay? So because this indicial equation is actually the condition for the very first n equals to 0 to be 0, if you use the correct values of the indicial equation, you will always find that n equals to 0 term will add up to 0. Okay? So that's the beauty of it. Okay? So that's always 0. And therefore, what do we have? We see that this here now should be 0. Okay? We have already observed that this is 0. Therefore, the only way that the entire thing could be 0, see on the right side it has equal to 0, right? So this plus this has to equal to 0 for some infinitely many values of x inside some interval. And the only way, there's a mathematical theory which says the only way that can be possible is when all the coefficients are equal to 0. So this has to be 0, this has to be 0. This is already 0, and therefore the only thing that we require is this has to be 0. And this is a good thing because that already shows us that's going to give me what? A recursive relation, right? recurrent relation. Okay. So let's continue on. We're not done yet. We still just have the recurrent relation. Okay, so let's try to simplify this. So what I'm going to do is, for the first three terms, since they have an in front, I'm just going to factor the an out. So the first three terms is an times n minus 1 times n minus 2 plus 5 times n minus 1 plus 3. And then the other one is minus an minus 1. That's the coefficient of some terms, and therefore this has to be equal to 0. Now you want to solve this for the higher an, so that an can be expressed by the previous term. So if you know a0, that will tell you what a1 is, what a2 is, what a3 is. That's how you use this recurrence relation, right? Okay, so let's continue on and simplify this. An times, this is n squared minus 3n plus 2 plus 5n minus 5 plus 3 minus an minus 1 equals to 0. And that's an, let's see, n squared plus 2n, and then the constant terms vanish, right? So it's really n squared plus 2n equal to an minus 1. I move this to the other side. And then I divide by n squared plus 2n, an minus 1. And then I can even rewrite this by factoring the denominator as an equals to 1 over n times n plus 2. An minus 1. Now, when does this start to hold? Is this true for all n? No. For n greater or equal to what? 1. 1. Okay, because this was inside the summation. Recall that this was inside the sigma and from 1 through infinity, right? So since this was inside this n equals to 1 and after, this is really true only for n 1 and after, okay? So if this was 2 and after, then you should put the condition 2 and after. If this was 3, then you should put it as 3 and after, okay? So that's something that you should always be aware of. Okay, now let's actually get to use it. So for example, if the exam question was, if I give you this equation and say, find the recurrence relation for such and such, you stop here, because that's the recurrence relation. Now, if you're told to find the actual Frobenius solution for this r value -1, then you actually have to use this recurrence relation to figure out what a1, a2, a3, all these are in terms of a0. Okay, so let's do that. So let's see what that recurrence relation says when n is equal to 1. That means a1 is 1 over 1 times 3 times a0. Right? Okay. For n equals to 2, that's a2 equals to 2 times 4 times a1, which is, by the way, 1 times 3 times a0. Therefore, this is 2 times 1 and 4 times 3 over 1 a0. N equals to 3 gives you a3, 1 over 3 times 5 a2. And because a2 is this much, if you multiply 3 to this and 5 to this, you get 3, 2, 1 times 5, 4, 3 of a0. Okay. And sometimes it's hard to find the pattern, but for this one, it's easy to find the pattern, right? It's always 3 factorial, right? And this is almost 5 factorial, provided that you multiply 2 top and bottom, right? So you have 2 factorials here, 3 factorial and 5 factorial. And I think you can guess what an is in general. Okay, so an in general, if you look at it, here's 3 and we got 3 factorial, so what do you have? N factorial here, okay? And then here's 3 and that's 5. What's the relation? 2 and 4. What's the relation?
N
Huh?
plus 2.
N plus 2 factorial.
N plus 2. So you're going to get n plus 2 factorial, and you should put a 2 there. Okay. So this is like one of these ideal cases where you do find a relationship. And in fact, that's how mathematicians can, in general, come up with these solution for any n. And once you have this, you can, it's possible to express it as a function. So let's just continue and write it as a function. So since an is this, now I can plug this in here. And for the exam, I would usually just say find 5 non-zero terms or something, so you don't have to find this pattern of like finish at A4. A4 will give you the 5th non-zero term or something, okay? Yeah. But let's just see how we can solve this to the end. Okay, so we have y equal to sigma n equals to 0 through infinity of 2 over n factorial times n plus 2 factorial times a0 x to the n minus 1. Okay. And you can even factor the a0 out. And you have a nice solution, right? And what mathematicians will do after this will take this and name it. Like, since we found it together, maybe we're going to call this maritime function or something. And then we have, we can calculate the values by approximation. I mean, if you need to say, so if I call this the function maritime function, and if I want the value m of say 3 or something, then just calculate this series for n equals to 0 until maybe 1,000 terms using a computer, with x being 3. And you can actually calculate it. It's possible. Okay? So it's I'm trying to say that you really, indeed, you really get a solution to the given differential equation this way. Okay? It's useful.